Hello everyone. Today I will discuss about the sorting algorithm. This is the part one. That means like there are various method of sorting. So we will discuss a few methods here. So first is introduction of sorting. So what is the sorting? Sorting is the process of transforming a given set of objects to take a specific order. That can be ascending order or descending order. So we know that if we are having some set of objects or data or any other items, if we are transforming that set in some specific order, that will be ascending, alphabetically ascending or numerically ascending. So any kind of ascending or descending order, that is called sorting. So the main purpose of sorting is to search for members in a sorted set. So if we will have a sorted set, then it will be easy, or it will be less time consuming to search an element or any object in a large data set also. So for example, why the sorting is important, we can just see some examples if we have the telephone directories, which we are very used to for the telephone directories earlier. So these contains large volume of data, very we can say large number of the contact details are there. So they are arranged in lexicographic order. So it is easy to search any contact or any phone number in from their directory. But assume if it is not in sorted order, what will happen? How will we search any contact or any details from there? So that's why sorting is very important. Similarly, in case of income tax file, you need to search any file, you need to place any file. So the sorting is very important there. Index entries in a book. So we can see here this kind of indexes are there in the book. So uh, they are in the alphabetical order. So that's why we can easily search any topic. Otherwise, it will not be easy to find anything from any index. Same in the case of dictionary are alphabetically sorted. That's why we can easily work with them. Sorting files on a computer. So files are sorted, then it is easy to find out or place any file. So that's why these are some example why sorting is important in our day-to-day life or in computers life. So broadly, we can say the sorting are internal sorting or external sorting. So we call the internal sorting is like sorting of arrays. So what is sorting of arrays? Uh, it is done in the data set present in the internal memory of the computer. So it is required for economical use of economical use of our available store. So this array sorting is very much useful for economical purpose also. Our memory can be used in a very optimized way, and as it is done in internal memory, so internal memory is very fast, so this sorting is very fast. These are some method of sorting of arrays. Similarly, we can say one more type of sorting is sorting of sequential file. So that sorting happens in external, that is called external sorting also, as the sorting is located on slower but more spacious external devices. So external devices like hard disk, earlier we were having tapes also. So that kind of space we are using, so we have more space in those type of devices, but that is slower compared to internal memory. So um, in the array, like in the internal sorting, we have the element like some cards are present. Present on the table surface, or we can see this the picture which is below the stack of files. So these kind of arrangement are there for array sorting. Like we have the element, all the elements are accessible, and we can see all the elements. So accordingly we decide some sorting algorithm. But for the stack, like for the sorting of sequential file, we have the different pile of files. So they are like, we can see three type of pile are there. So we can only see the first or top desktop file there. So we use the sorting algorithm according to that only. Next we will discuss about the sorting of arrays. So in this talk we will just talk about a few methods of sorting array only. So sorting array is happening in internal memory, that is called random access memory. So we as we talked that is a fast memory, faster way to access the RAM. And so sorting in the sorting we will discuss the how the sorting is important and how we do the sorting. But the important thing is there are multiple sorting algorithms we have developed. So how to measure which one is good or which one is bad? So mainly a good measure of efficiency is obtained by counting the number of key comparison, which is denoted by C, and moves or transposition M of the item. Does it mean? If you are having some unsorted of data set or unsorted array, so to sort that array, you have to do some comparison of the elements, then you have to move some elements. So the more the number of comparison and more the number of moves, the time complexity will be increased, and it will take more number of more number of hours or more time. But if the count of comparison is less and moves are less, then it will take lesser time and the time complexity will be lesser. So that is a measure of efficiency of the sorting array algorithm, how good is the algorithm. So there are multiple methods. So we will discuss about straight methods. So straight methods, complexity of straight methods are in order of n square. So n is number of element of the array here. So the complexity comes in the order of n square. Then also we will discuss about the straight methods because they are easy to understand, easy to implement, and they are short. So for introduction, or we can say easily understanding the sorting algorithm, we use the straight method. Although their complexity is n square, but for the sake of understanding, we will discuss about those straight methods. Also, these are very well suited for exhibiting the characteristics of sorting method. So, it is easy to show the exact characteristics of that sorting method by using those straight methods. So that's why we discuss about the straight methods of sorting. So these straight methods are classified into three parts, three type of sorting. So one is sorting by insertion, second is sorting by selection, and third is sorting by exchange. So in this talk, we will discuss about sorting by insertion only, and sorting by selection and exchange we can discuss in some next talks. So is there any doubt till now? If any question is there,
no,
or I can just move.
I don't have.
Okay. So sorting by insertion. So we will understand that how we do the sorting by insertion, and what is we will understand it by with one example. So first, what is insertion sorting? Like we will pick an element from the array and we will insert the element into its we will insert this element on its appropriate position. So that's why it is called sorting by insertion. So just pick a one element and keep it on appropriate place. So how to find that appropriate place? That is a part of algorithm, and that will decide that how efficient is the algorithm and how many number of counts are there and how many moves are there. So here we are having one array, and the numbers are 23, 12, 81, 19, 08, 78. So this is an unsorted array, and we have to sort it in ascending order. So what will we do? We will in this algorithm, it starts with the place 2. So the number of elements are 6, 2, 4, 6. So we will say like n equal to 6 here, and we will start from the position 2. So we will denote the position with I. So we will start with I equal to 2, and at the position 2, the number is 12. So now it will take I equal to 2, number is 12, and it will compare the 12 to its left element. So if it will check if it will compare with that element, and it will check whether it is greater than or less than from the left element. If it is less than the left one, then it will go to the position will be swapped. Or if it is greater than the left element, then there will not be any change. So it will be swapped till the position till the point where it find the element which is less than itself. So how will it work? It will compare 12 to 23. So it will find that 12 is less than 23. So swapping will happen, and 12 will go to position 1 and 23 will go come to position 2. So it will come like that. Okay. So next is it will come to I equal to 3, that is 81. Now it will check for 81, and it will check with 23. So it will check that 23 is less than 81. So that means it is already in sorted order. So nothing will happen in this position. So only one comparison will happen with the 23, but it will not be swapped. Now it will go to I equal to 4. So I equal to 4, it is 19. Now it will work. It will compare 19 to the element on the left side. So it will compare 19 with 81, and it will check that 19 is less than 81. So it will move 19 to 81 and 81 to 19. So the position will be swapped, and 19 will be at I equal to 3. Then again it will check, it will compare 19 with 23, and again it will find that 19 is less than 23. Then again position will be swapped, and 19 will be at I equal to 2. And 23 will be at I equal to 3. Then again the comparison will happen between 12 and 19, and it will find that 19 is greater than 12. So now there will not be any swapping will happen, and the final position of 19 will be I equal to 2 in this move. So how will it happen? At I equal to 4, the 19 is coming here, and 23 and 81 are shifted on the right side. So that is sorted array till I equal to 4. Now we will move to I equal to 5. So now we come to I equal to 5 element, that is 8. So it will compare 8 to 81. So 8 is less than 81. So the position will be swapped, and 8 will come here to I equal to 4 position. Then it will compare 8 to 23, and it will find that 8 is less than 23 also. So the position will be swapped, and 8 will come here, and 23 will come at I equal to 4 position. Then it will compare 8 to 19. Then it will find that 8 is again less than to 19. Then 19 will come to I equal to 3, and 8 will come at I equal to 2. Same thing will happen when it will compare 8 to 12, and it will swap the position for 8 and 12 also. So what will happen? 8 will come to I equal to 1 position after comparison with all the four elements, and all the 4 moves will happen here. So it will be like that at I equal to 5. So now we have the sorted array of 5 elements. Now the last element I equal to 6 is there. So it is 78. The same thing will happen. It will compare with 81, and it will find that 78 is less than 81. So the position will be swapped, and 81 will go to I equal to 6, and 78 will come to I equal to 5. Then it will compare 78 to 23. As it is greater than 23, then it will not be swapped further, because we know the array is sorted. So now the 78 will be at I equal to 5 only. So this is the last swapping. So now we got the arrays sorted. So now we got 8, 12, 19, 23, 78, 81. So this is the algorithm of sorting by insertion. We are just taking one element and comparing it with other element, and searching and inserting on the appropriate position of the element. So here we found, so there are some comparisons, there are some moves. So we will just check how it is working. So these are the final moves represented here. So there are 1, 2, 3, 4, 5, and 6. 6 passes are there where like we have worked on. So we can say there is for loop for ix in test array, insert x at appropriate place. So what it means, in the test array, it will work for all the elements which will start from 2 to n. So the loop will start loop will run for all the elements. If the number of elements are n, so the loop will run for n times. And then what will happen? First, the 12 will be swapped. So one, it will come here. Then the next step, 81 will be here only. It will be compared with it only. Then 19 will be compared all the elements. So it will come here. Then 8 will be compared with all the elements and it will come here. And then 78 will be compared with this element and it will come here. So inside this loop also, like this outside loop will run for n times, and then inside this loop also we are comparing the n elements again. So that's why the complexity will be in order of n squared, because n from the outer loop, and in this outer loop we are comparing the n number of elements with themselves. So it will go to n square. So we can discuss in the best case, worst case, what will happen. So in this case, best case will be when array is already sorted, and worst case will be when array is reversed. So we can discuss how will the moves will be there. So just I will show you in the sorted array and reversed array what will happen. So please tell me if it is visible. I'm just writing something. So is it visible? Hello?
Yes, ma'am. It's visible. R is written.
So I'm just taking one array which is already sorted. So we can take 2, 4, 9, 12, and 18. So what will happen here? We have we have to do insertion sorting here. So we can take one more, 20. Okay, it is already sorted. That is the best case. So how many comparisons are there? I will show you. So what will happen? It will start from I equal to 2 from the 4. So it will compare with the first element, that is 2, and it will find that 4 is greater than 2. So only one comparison will there and no move will be there. Okay. So it will be like that only. After that, it will compare 9 to 4, and it will find that 9 is greater than 4. So only one comparison there, and there will be no move. So now it will not compare further, because it has find that it is greater than the left element. Again, it will compare 12 to 9, and it will find that 12 is greater than 9. So compare will be 1. Same comparison count will be 1, because 18 is greater than 12. And then for 20 also, 18 is greater than 20. 20 is greater than 18. So compare count is 1. So we will found that 1, 2, 3, 4, 5. There are comparison count are total comparison count are 5. That means number of element are 6 and comparison count are 5. So in the best case, the comparison count will be n minus 1. Okay. So if best case will be there when the array is already in sorted order. Now we can take one worst case, like array is in sorted in reverse order. So how will it happen? Like we will say 9, 8, 5, 4, 3, 2. That is the array. Now we will check, it will check 8. 8 is less than 9. So there will be one comparison, and it will be swapped the one move. So it will be like that: 8, then 9, 5, 4, 3, 2. Now it will come to I equal to 3. This position, it will check that 5 is less than 9. So one comparison will be there and one move will be there. And then after that, it will come to I equal to 2 position, and it will compare with 8. And also it will find that 5 is less than 8. So one comparison is there and one move is there. So total comparison count will be 2 for this element. Same, now it will be like that: 5, 8, 9, 4, 3, 2. Now we will come to I equal to 4. So the element is 4, and it will compare with this. So C equal to 1, and it will be swapped. Then it will compare, 4 will be compared here. Then it will be swapped, and then 4 will be compared here, and it will be swapped. So C equal to 3 for this element. And then in the similar fashion, we will do for 3 and we will do for 2. So we can see for every element, we have to compare every left element in the case when the array is in reverse order. So when we will calculate the complexity of this, we have to run the loop for the n square times, like the outer loop for the n times and then inner loop for the n again n times. So the complexity will go till n square. So that is the worst case in the scenario. So how how the insertion sort work in worst and best case. So we have just seen there here. So is there any any question?
So I just need a small clarification. Hello, am I audible?
Yes, yes.
Okay. So whatever you have shown in all these 5 rows, starting from 23 to 78, let's suppose you have explained it, and I believe I followed it correctly. So if suppose you have write down one code, whatever you are trying to write, or in the right hand side, so will this insertion will happen at once, or it will take as many steps as you are explaining manually?
Sorry, I didn't understand. Like what I'm saying, like we are inserting an element at right.
No, I'm telling, let's suppose starting from 23, 12, 81, 19, 8 and 78. Okay. So finally we have inserted after 5 different steps. So in the ascending order.
Yes.
Okay. So whenever we will write down a code, so will it automatically take every element at once, or it will do step by step, the way you have explained to us?
Yeah, so it will do step by step. So we
Okay.
do these things through loops. So the first for loop I have shown here for x in test array. So that x
Okay.
will traverse through all the array in test array. So it will start from 12. If we will write the proper
12.
code, we will start the loop from I equal to 2 to 6. So it will traverse all the elements. Yeah.
Okay.
And then inside this loop, we will compare this element to I minus 1 element. That we will give this the position I, and it will be I minus 1. So we will compare I to I minus 1. Then again we will increase the value of I. So then again this will be I, and it will compare I to I minus 1. Then if the swapping will be happen, then it will be I, and it will compare to I minus 1. So that kind of thing actually we will do in the code only.
Okay. Okay. Then I equal to 3, I equal to 4, and so on.
So I will be incremented in every pass of the loop. So
Okay.
then we will write the logic that if there is a swapping, then the value of I will be again 2, and then we will compare to 2 to 1, and then again it will be decremented till the last point.
So the last element.
Okay. So it will so that's why the outer loop will go through all the 6 passes, and inner loop will go to depending on the swapping. So if there are 2 swapping, it will work for 2 elements. If there are 4 swapping, it will work for 4 elements. So that kind of thing inner loop. I have not written the code here because it would be technical for that. That's why I have not written the code here.
Okay.
Yeah.
Okay, I understand. Thank you. Okay.
Okay. Okay, so
Ma'am, I have a question.
okay.
In the previous example where the sorting was worst, right?
Uh-huh.
The complexity is n square,
In order of n
right?
square, it is not exact formula. There's a formula for that.
Uh-huh.
So the formula is of order of n square.
Order of n square. What is n here?
N is total number of element.
So in that example, there are 6 elements.
Mm-hmm.
So there should be 36. The order should be 36.
Yes, yes. So the like in order, like we can, I can explain like if you will do the sum of the count now, which I have already shown, like one for like first element, I have shown that there. I have one minute. I will show you again.
Means
So
total
here,
I'm counting there are 15. C is equals to 15. I can count. 36 I'm not able to count. Like this is C is the value now which we are saying n square.
yeah, it is not n square. It is order of n square. So what we can see, like in case like first in the first move there it was 1. Then for I equal to 2, the count is 2. Then for I equal to 3, the count is 3. So we feel found that if the total number of n element, then it will be the sum of n minus 1 element. So the sum of n minus 1 element will be like n into n minus 1 divided by 2. So it will like the sum of first number are n into n minus 1 divided by 2. It is like that now. So it is coming like, for in the worst case, it is coming like sum of n minus 1 numbers. So it is like, is it visible which I am writing?
Yeah, it is visible.
Yeah. So it is like that, n minus 1 divided by 2. So it is like we will do some calculation, and it so here you can see it is coming in order of n square. And in the best
Okay.
case, it was coming like c equal to n minus 1. So it was not n
Oh,
square order. So that is the meaning
okay.
of that n square.
Okay. Means the total number will be n minus 1 by 2. That is correct.
Yes,
That's
yes.
correct. 15. Okay.
Yeah. So this is because if we have counted in the specific this case, that is the worst case. But if you will talk about the average case, so it can be like any number of moves. So they have like generated one formula for there also. So it also comes in the n square order, like in the same terms, like 1/4 is there. So I don't remember the exact calculation of how we do that, but it also comes in the n square order.
Is the sorting is always in ascending order? It can be in descending order also.
Yeah, we can do in descending order. Then we have to write the logic in different manners. Like
Logic will be different.
But yeah, similar. If it is an insertion one, we have to do in a similar fashion. But yeah, logic will be different. We will start with the end, and like we will do some different. Like we will increment the I. So some different thing will do this. But the logic will be quite similar to that. Only the starting point, ending point will be different, and the increment or decrement I will be different.
Okay.
Okay, so next is, okay, so then now as we have already discussed, like like it is complexity is order of n square. Like we are every time comparing every element to other elements. So if element is at the 5th position, we are comparing this element to all the 4th element if it is less than all the 4 elements. So like time complexity is increasing, but we can improve this insertion sorting algorithm by by using binary search. So in binary insertion sorting, we use binary search algorithm. So it improves its complexity to in the order of n log n. So earlier it was in order of n square. Now it will be in log n log n order, because the we what we will do, we will just sort, and we will just sort the array before some element, and then we will just compare the first element of the sorted array. So how will we do that? I will show you in next step. So first to understand the binary insertion sorting algorithm, we will first understand how the binary search algorithm works. Because the binary insertion sorting works on the principle of binary search algorithm. So binary search algorithm is the first how why or and how we use the binary search algorithm. So in some array of some elements, if we have to find out the location of any element, or we have to find if the element exists or not in some array, we use the searching algorithm. So to search any element in an array, you have to do some comparisons. Like you will traverse to the one thing, like you can traverse to the all elements of the array. You can compare the element which is to be searched to each element of the array, and whenever you find the element, you can stop your searching. That is also one way. So if the array is very large, the comparison will be very high. So in the binary search, we take assumption, or it is not assumption, we have to take the arrays in a sorted manner. So if the array is already sorted, then we will search our element in the basis of the divide to divide the sorted array. So how will we do that? I will just show you. So let the array is, we have taken the array of 10 elements, that is 2, 3, 10, 12, 23, 34, 45, 58, 60, and 80. There are 10 elements in our array, which is in sorted order. Now I have to find out if the 58, if there is a number 58 which exists in this array or not, or we can identify the location, where is it located. Anything we need to search on this array, that 58 is there or not. So first thing, what we can do, like we can just take this 58 and we can compare with first element. Okay, 2 is not equal to 58, then 3 is not equal to 58, then 10 is not equal to 58. So we can compare this 58 with each element. Then we will go till this point. Then we will find that it is present at 8th position and it is present in the array. So it is very much time consuming. We have to compare all the elements. So if we can find any improved version of it, so how we can do it? Because we have already taken the sorted element. How can we do that? We will just divide this array into two parts. So how will we do that? The element are 10. So 10 divided by 2, that is 5. So we will divide the array into 5 elements. So first 5 is here and first 5 here. So these are sorted. So 2 to 23 is there and 34 to 80 are here. Now we will just take the fifth element, the half, like fifth one is the half, mid place we can say. So we can compare the mid of the element to 58, which we need to search. So we will find that 23 is less than 58. So the array is sorted. So we know that 58 will not be in this list, this left side of list, because the last element of this half array is less than 58. So we have not to compare the 58 to all these elements. So what we will do? We will just ignore all these 5 elements and we will work on the right side of 5 elements. So we will search this 58 in the next 5 elements. Now we have the 5 elements array where we need to search 58. So we again apply binary search here, and we will divide 5 divided by 2, and we will get 2.5, and 2.5 cannot be a place value, so we will take floor value. So it means we will take the second value, means 5 by 2, floor value will be 2. So we will take I equal to 2 position. So how will we do? We will come here. I equal to 2 will come here, 34, 45. So we will compare the 45 to 58. So we will find that 58 is again greater than 45. So we can ignore all these 34 and 45, both the element. We don't need to compare here. We just go to the next part of the next part of the array. So again, we have the 3 elements, and we will just divide 3 by 2, and we will get 1. And 1 is the 58. To first position, we will compare 58 to 58, and we will find the value 58 is there and the position of that. So now in this method, we can see we have not compared the 58 with all the elements. We just compared first 58 to 23, and we have ignored these 4 elements. So the 4 comparison are reduced. Then again we have compared 58 to 45 only, and then we have ignored 44. So again one comparison reduced here, and just we have found the 58. So you can understand the difference between the normal search and binary search. If we had to compare with every element, then it would be 7 comparisons. Now it is only 1 or 2. Third comparison we found it. Okay, so it is very efficient method of searching. Okay, so any question here in binary search, so that we can move to binary insertion. If it is clear, then it will be easy to understand binary insertion.
It's clear to me, ma'am.
Okay. So this algorithm, binary search algorithm, we use in binary insertion sort. So we just make the left-sided array as a sorted array, and we just use the binary search method in inserting an element to the appropriate place. So what does that mean? The insertion algorithm, what does it do? It takes one element and keep the element in an appropriate place, like insert the element in the appropriate place. So to find that appropriate place, we use the binary search algorithm. So for that, we just make the left side array a sorted array. So how will we do that? It will start from I equal to 2, that is 12. It is the same array which we have taken in the first example of the insertion algorithm. So 12, to left side of the 12, there is only one element array. So one element array, we cannot divide it by 2. So we will compare it with the 23 itself. So we will find that 23 is greater than 12. So swapping will happen and comparison will be 1. So it will swap. Okay. Now we come to I equal to 3, that is 81. Now the array left side of 81 is 12 and 23. That is of 2 element array. In 2 element array, it will do the binary search. So it will just compare 23 to 81. It is not there is no swapping required, so it will not swap here, and it will. Oh, sorry. Okay, let me do it again. Okay, so 81 is there only, and now we will come to I equal to 4 position. So I equal to 4 position, it comes to 19, and 19 have 3 element array before it, that is left side. And now to get the proper position of 19, we will use binary search. So now here we have the three elements before 19. 3 element array is there. Now we will divide the 3 by 2, and we will get 1.5. Floor value will be 1. So now first we will go to I equal to 1 position. So 1 is 12. So 12 is greater than 19. So we will find we will ignore the left side element, and then we will compare to 19 to 23 only, and we will find it is less than 23. Then it will be inserted here only. Okay, so it will come like that. Now we have the 4 element, like it is sorted element, and we have the 4 element array, and the same thing, the binary search will be used to insert the element 0, 8. So now again we will do the binary search here, and binary search, the array will be divided into 2 parts. So the 2 elements will be there, 2 elements will be here. So it will check that 8 is less than 19. So it will ignore 23 and 81. It will just check 12 and 19. So 19 is greater than 8. So it will just again divide this 12, 19 array to 2 parts, and again it will compare 12 to 8, and it will find 8 is less than 12. So it will be inserted in at the first place. And the same thing will be happened with 78. It has a 5 element array which is sorted on the left side, and will use the binary search algorithm and divide it in 2 parts and again 2 parts, and then we'll compare, and then we'll move to 78, like before 81. So that will be a sorted array. So here the difference is like that. The comparison was lesser than the previous one, because we have divided the array to compare. So we have not compared with every element. So that's why we can say it is improvised version of the previous insertion sort. So that's why the time complexity is lesser for it. So that is a small comparison of the insertion sort, the basic insertion sort and the binary insertion sort. So we can say that binary insertion sort is an improved algorithm in terms of comparison and time complexity. So the search interval is half for an item. So the comparison count comes like sum of log I. So log is base 2 here. So accordingly they define it like every time log to the log base 2 I is the comparison count for a ith element. So for all the elements, the count will be sum of these log I. So for calculation of this, they do the integral from 1 to n, then they get some values, and order comes in the complexity comes in the order of n log n. Okay, so it is like quite lesser than n square. So but we can say like, so the comparison is lesser than the previous algorithm, but number of moves are still in order of n square, because moves are again the same we have to do. So like not the same, it is also lesser, but it comes again in the order of n square. So we cannot say that overall performance is very much, there is a drastic change in overall performance. Obviously, this is the better approach, time complexity is lesser, but there is not very huge change because the number of moves are not very much reduced, but still the comparison are less. So that's why this is the improved method of from like, this is the improved version from the basic insertion sorting. Yeah, so that was the difference between these two insertion algorithm. Yeah, so for in this talk I have only covered this insertion sort algorithm. For the selection sort and exchange sort, I can cover in later talks. So that's all from my side. Thank you.